Welcome back to another video. So there has been a year since I made the last video and basically got exhausted, didn't want to do them anymore for a while or anymore, I don't know. There you go. There has been a year ago since I did this video, and last time we looked at the register here. But we also did a simulation for bus available. We also saw that bus availables comes in on this sprite and sets off like a domino effect on each sprite. So if I start blocks here, you can see, you can see here is sprite 0, sprite 1, sprite 2, and so on up to 8. So there's 8 sprites, and there's an enable signal traveling across here. So these are counters. So what are they counting? Why am I looking up in this area? Well, you can see on my file it's an address generator.svg file, and up in this top corner of this dieshot we have address generators. So if we're going to have data fetches, we need addresses. So I started looking at it. I got more interest to do it. So here you can see CB13 and 11 and VM13 and 10. Those are the upper bits which selects banks for graphics and for character pointers. I started looking and I was thinking, okay, I don't know what all these things around here is. And now I have painted something here, but before I did that, I didn't know what this was. So this area here has been a mystery for me a while. And these are, I haven't reverse engineered them, but I know they are sprite counters. So I think they are counters also. Well, let's get into it. So down here, I started looking. What is coming in on this register? This is the last register. We have looked at all the other registers, but this one is the last. So we have some enable signals coming in here, and the reason why I can see that is because this is an output driver from this register, drives an internal network, which I will talk about in a minute. And the reason why it's enabled is because this long net up here can pull it to ground, and when it pulls it to ground, it can't put any zeros out on that bus. It's a wired OR thing. So, and the same happens over here. But we can also follow this line. It says A11 there, and I will show you shortly why it's called that. Then up here is on the video matrix upper address bits. You can see it's connected together. So there are not only one driving this network. And if you follow it, you can see it goes up here, the third from the top, and the third from the top goes up here, and then up here, and you can see it splits into two directions. We have another driver here. Look. And it goes further, and I think from here it just goes out to the pads, so we can follow it, but trust me, it just goes out to one of these guys, not this one, but one of them, so which are address pads that goes out to the pins. Well, this is a counter. We can actually cheat a little bit, because if we look at the VIC2 description, we can see that in this area we have C, which is character address counters. Now we know that there's an internal network that drives, which are driven by different modules in the system. Then I was thinking, how is this address thing composed? So you have an upper bit, which are controlled by this selection in the register, And the thing I followed was up here. You can see they are going on top here, and then it's shared with that one, and it just passes right out of the pad. But when you come to think of it, this video matrix, which is a 40-bit long, when you think of it, they contain pointers to characters. Like A would have one pointer, B will have another pointer. So that comes directly in on one kind of data fetch. But when you come to think of it, a character on the screen is not just a pointer to the character, it's also pixels. And also, the screen is drawn line by line, so that character is sliced up into 8 slices. So I started counting, and this register has, I think it was 4 or 3 upper bits. And then I was thinking, okay, then we must have some output from the video matrix. So now we're talking about graphics access. And sure enough, we know that these 4 upper ones are colors, so that goes to the color register, but the lower 8 bits, they also go further out here. Not sure where they go now, but you can also see they also go down here. And they are also on the internal address bus, but on lower values. But that's not enough. We need to slice them up in 8, right? So therefore you need a 3-bit counter, which I believe is down here. You can see, let's see if we can, yeah, there's an address line, this one. So that's the whole address. We have the upper bank selection, we have the character selection, which comes in here, and we have the counters to keep track of which slice of the character it's displaying. Now, that's not enough. We need something to fill this buffer also, right? Because we have 1000 and something characters on the screen. So we need 1000 pointers or something. Yeah, so somewhere in memory there will be 1000 pointers. There will a whole set of characters for the screen. Not the graphics, but the characters. So that's where this 10-bit, I think it's 10-bit counter is. To be able to put an address out on the address bus, we need to do it at a certain point. And this is where it becomes a bit difficult. So we have here all the lines coming in, and we can see some weirdness going on here before it actually comes out on the internal bus here. So let's have a look at that. So they come down here. There's a pull-up up here, and if all those used transistors are on, that means this network is on anyway, then all of them will disable everything. Everything will be low. All these outputs will be low. So that's an enable. So if they are low, then the signal coming from here will be inverted. However, it will come out here. So this driver will actually do something on the internal bus. So I started looking in another place. And this will be like a recap from previous videos. It's been like 4 years I've done these videos. Long time in between. So what we did in the very first beginning was, well, at the very first beginning, I looked at only pads, just to identify what is on each pad. And now that was a very easy task, because, you know, if you line up an IC, you can see that the pads are drawn out logically from the pad to the nearest Yeah, and it's arranged in a logical fashion, as you can see. But the second thing I did was finding out that this must be some kind of address decoder, and I figured out that if I put numbers on it, I actually got a match on which address was what. So that's another file, but anyway, so like this one, and this one is another register. It has a comparator. There's data lines coming in on the register. There are read and write signals. So all of that we have seen, and then you have comparators, because these are sprite position registers, so they compare with the position, which is actually this counter over here, which we have simulated, by the way. And what happens is that when a counter, there's a match, you will have a something happening elsewhere, so it's a timing circuit. So we simulated it, and we saw that this was actually a synchronous counter, so that was cool. We kind of knew it, but was nice to see. Also, right next to the counter, there's a room. When a counter has a certain value, these lines will light up when they have the same value as the counter. For example, this is display enable, so it is mixed together with a register called display enable, display bit. And when that matches together with this enable thing, you can get a latch down here, which sets something else. And in this way, we can know what to do at a certain time, or the VIC can anyway. So just a little recap that there. So let's get back to what we were looking for. So I was looking for an enable signal. There's a signal coming in, which I had drawn, which goes all the way up here through the whole counter. So that's an enable signal. And you can also see it goes past this decoder. It doesn't have anything with the decoder to do. It comes down here. Let's go in on it. Yeah, so let's see. Yeah, there it is. It goes here, here, and here. And it's driven by this net, which is, again, I haven't drawn this part yet, but driven by this one, which comes from this one, which something magic is happening here. I think something to do with the two clocks. Something is going to happen in a certain order, or delayed order. But look, this line here, this is a network, or a metal network that goes through all of this, and to this one. So check this number, which is, this is the other counter, the one that chops up the horizontal line, which for some reason I have called vertical. Anyway, I'm not sure what's vertical and horizontal anymore, because it certainly is different in this image that I showed you. This line comes in here, it says 188 and F. That's also interesting. So alright, so I was looking, and what I come to a conclusion was that this is a vertical increment. It makes a lot of sense. And also, it is set at one point, and like, I think it's 8 cycles later, it's turned off. And the reason I can see that, because this is a 10-bit counter. And let's see, here we go. It goes down here. Here it's not connected to the counter. So that means for 8 cycles, it doesn't do anything. So that means that the signal is on for 8 cycles. Well, for 8 pixels anyway. For 1 pixel takes is on the 8 megahertz clock. So basically it's for 1 character. So I think what's happening here is that the signal comes up here, and other places by the way, but up here also. And this counter will count for one character for every line, I think. But that was interesting to see down there anyway. So this video is getting a bit confusing. So what I want to do in this video, and maybe the next one, let's see, is to actually simulate the whole signal. The signal coming up here. I don't think I can simulate everything, but there's some inputs here that I don't know what is doing. So, well, I can see them come in here. Like, you see this one? If you go up to the next bit, you can see they are the same. They are like, they connect together as like an output of something, a gate or something, into the next bit of the counter. And so. And that's okay, but it comes from a place I don't know what is yet. It seems to be the same one that comes in here, but it's like delayed or something and mixed with another signal, which I don't know what is. So I will have to look that up. But I will decompose this circuit. This is now in layout form. I will go to transistor level, and then I will go to block level, or what you want to call it, and then I will simulate it, and then we will see that this thing is actually counting. I really hope so. It worked out really well for these free running counters. It's X and Y. I call them X and Y because that is usually what you call them, or I've seen what you call it in video games, in graphics chips. You have X and Y counters. Another funny thing about this counter down here you have 8 megahertz down to 1 megahertz on this bit, but there's no clock division. Oh, sorry. There's no counter here. These are synchronous counters, but why don't you have it on the two lower bits? Well, what I do is that I just divide the signal into up in the clock circuit. Up here, there are dividers in here. There's really large clock drivers, which are 8 megahertz, 4 megahertz, 2 megahertz, and 1 megahertz. So when you're dealing with a synchronous logic, you don't want things to just happen whenever they happen. You want them to be synchronized. You want the state to change at the correct moment. That means you prepare the state so it's a bit glitchy and stuff happens, and then boom, you put the value out, and then it's rock solid for the next state, which is when it matters. When it's changing, it doesn't matter so much, but when it's ready, it should be ready. So that's why you have a synchronous counter, I think. That's my take on it anyway. I'm not an expert. And thank you very much for watching. I think I will do the simulation at another time. And I really hope you enjoyed this, because I did enjoy making it. Here, these networks which are driven by these things I talked about in the beginning, in the wired OR thing, they come in here actually. And this thing here goes into some logic here, and then it drives the address pad over here. So this is a push-pull driver. This is a circuitry for enabling it. So you have a bus available thingy going up here. And this is a multiplexer, or 1-bit multiplexer. But together with all the other pins, it becomes a multiplexer. So it's a 2-input multiplexer. I'm not sure what the other input is, but that's a multiplexer anyway. So it shares that pad. Oh, the answer is here. You can see this is also A8 and A0. So I think this is the A8 from something. We will find that out. Why do we have A8 there? So we will have to do simulation. And the thing I was going to say about the simulation was, when you make the simulation, you make logical blocks. We have a abstraction away from layout, transistor level, makes it all worthwhile. So thank you very much for watching. I think I will end it there, and see you another time.